Is there any real difference between a computer and a human mind? As of today, I think there is a crucial difference, but we'll get to that later. Ever since Mary Shelley imagined Frankenstein, we humans have been fascinated by the idea of creating artificial life. So maybe AI today is just a modern version of Frankenstein. But could a sufficiently advanced computer ever gain all the capacities of the human mind? That is the subject of today's episode about computationalism. So let's get started. Computationalism is the idea that the human mind is quite literally a computer. But to truly grasp this theory, we need to know what it means for something to be computable. So let's discuss the Turing machine, named after the famous computer scientist and mathematician Alan Turing. In order to build a Turing machine, we only need 4 things: a machine table, a state register, tape, and a so-called head. The tape needs to be very long and divided into squares. The tape should actually be infinite, which makes the machine a practical impossibility, but we don't need to worry about that here. The head needs to be capable of performing these 4 tasks. 1. Interpret the symbol within each given square on the tape. 2. Switch symbol within squares. 3. Move between squares. Halt or stop all activities. That's it. And then we have the state register. The only thing it's doing is really storing the state of the machine. Don't worry, it'll all make sense soon. And lastly, the machine table is specifying the rules which the head acts upon. So here we have the full machine, and I've provided a tape with a specific sequence of 1s and 0s. So let's start the machine and I'll explain what occurs. The machine begins within the first state, which tells the machine to follow these 2 rules. If the head reads 1, then change nothing and move to the right, and change to state 2. And secondly, the rule of if the head reads 0, then change nothing and move to the right and remain within the first state. So in the first couple of squares, the head only reads 0s, which causes the head to continue to the right and neither change the symbol nor the state. But here it interprets a 1, which causes the machine to not only continue to the right, but also swap state, which means that it will follow a new set of rules, which are if 1, then change nothing and move to the right and remain within state 2, and the rule of if 0, then change the 0 to a 1 and move to the left and switch to state 3. The machine moves on until it reaches the next 0, which causes the machine to swap the symbol and change it into the third state. The rules of the third state is if 1, then change nothing and move to the left and remain within state 3, and the rule of if the head reads 0, then no change and move to the right and switch to state 4. The head continues to the left until it reaches the next 0, which causes the machine to move to the right and enter the fourth state, which gives the head the instruction, change symbol and then halt. Now, let's look at the tape. In the beginning, the tape looked like this, but now it looks like this. You might realize that what the machine has actually done is calculating 2 plus 3. And as you can see on the new tape, we find a set of 5 ones. Now, this was a very basic example of computation, but what's amazing about this machine is that it is basically doing math, right? And in principle, a Turing machine is capable of performing all the tasks of a modern computer, provided that the tape is long enough. Now, the thing with the Turing machine is that it is being rational, a trait that before was thought of to be uniquely human. For instance, Aristotle claimed that the defining feature of humans was rationality. But a Turing machine is rational, isn't it? So now, the question is, could it be the case that the human mind is working exactly like a Turing machine, following algorithmic rules depending on what inputs we receive from the outside world? But instead of ones and zeros, we have inputs such like a warm sensation or a cold sensation. What if we just switch out my brain with about 86 billion small people, one for each of my neurons, who are simply following Turing machine-like rules? Would all these small people be able to simulate my brain completely? Maybe, but there is one big problem here, and it is due to semantics. Let me elaborate. The thing with a Turing machine is that it is only really interpreting syntactic properties. For instance, let's consider this logical argument. If something has branches, then it has leaves. My company has branches. Therefore, my company has leaves. This argument is actually valid, but there is an obvious problem with it. If we change the argument into formal logic, a computer would have no problem whatsoever to conclude that this argument is a standard modus ponens argument. But what the computer misses is the semantic properties of the words. The word branch here is used with different meanings. In short, it has different semantic properties between the premises, which produces the fallacy of equivocation. But Turing machines can only interpret syntactic properties, i.e., the actual look or form of the symbol it's analyzing. To show why this problem is so severe for computationalism, let's look at a very famous thought experiment by John Searle. So, this is John. He is incredibly stupid. Oh, sorry John, didn't think you heard me. Anyways, John does not speak a single word of Chinese, but he is locked up in a room by himself in, let's say, Beijing. Suddenly, a set of papers filled with Chinese symbols slides into the room. John has no idea what they mean, but within the room he finds a book with a set of rules in English, which tells him how to proceed. John then begins to search for these exact symbols within the rulebook. Ah, he found it. If some odd symbols, then the same symbols and another set of symbols. He combines these symbols and slides it out. Outside the room, we find a Chinese man who began the whole process. The first set of symbols simply translates to "Hi," and the note that John sent out translates to "Hi, how are you?" The Chinese man outside the room thinks to himself, "Oh, the man behind the wall knows Chinese. How wonderful." But indeed, we all know that, in fact, John doesn't speak a single word of Chinese. He is simply interpreting the syntactical properties of the symbols and following rules, much like the Turing machine. Simply following rules does not grant meaning or understanding of the symbols. Therefore, the human mind simply cannot be a computer, since Humans are capable of interpreting semantics, which a computer cannot. But there must be something wrong here. If it is true that computers are only interpreting syntax, then an AI like ChatGPT would never be able to recognize an argument that contains an equivocation, right? But it did. It correctly identified the fallacy. So maybe it's just a matter of complexity. Maybe Searle is incorrect. But, importantly, there is a big difference between computationalism and what is called connectionism, which is more related to deep learning. But that is a topic for another episode. So if that sounds interesting, make sure to subscribe. Thank you so much for watching this video, guys. I really appreciate it. I put a lot of effort into this one, as you might have noticed. And there is some more fun and interesting animations coming up in the next episode about connectionism. So, thank you so much for your support. Take care. I'll see you guys soon.